Hi, I'm Olivia, everyone's favorite math teacher, and it's finally time to start talking about derivatives. So the limit allowed us to find the average rate of change at a given point, otherwise known as the instantaneous rate of change, right? So in our concrete example, that was the velocity of a ball falling from the Leaning Tower of Pisa at 5 seconds. That was a great practical application of the limit. Now, that's awesome for a specific purpose, but what we want to be able to do is not just solve one specific problem with one specific function. We want to be able to apply this technique to any function, potentially. So in order to do that, we need to make it generalizable. And when we do that, that means that we need to find some system or some method where we don't have to rely on specific numbers or specific functions. And, well, we kind of already did. All we do is we take what we know as the slope function, right? Which is the change in our range divided by the change in our domain. We take the limit as the x approaches the x naught. As we approach our points, they come together and find our answer. So that's very helpful, but it also kind of gives us a problem in that we end up having two x's. We end up having two elements from our domain. And typically in a function, we want to try to define it using just one element from the domain. I want to be able to just take just the time, right? Or just whatever our element is. So it would be much more useful if we could redefine this using just a single element from our domain in order to have a function. And it turns out, using one of our most versatile tools in calculus, we can actually do that. We're going to use a change of variables. And to do this, we're going to say, well, what's actually happening procedurally? What's the process that we're always going through when we look at the instantaneous rate of change? And it's that this denominator, the thing that was giving us the problem, is that it always goes to 0, right? So as x approaches x naught, this always becomes 0. And that was why we couldn't do it algebraically. That's why we had to create the limit. So let's just go ahead and work with it that way. Let's look at that distance as an h. So h is simply going to be x naught minus x. And we'll take the limit as h approaches 0, which is exactly what's happening. This is getting smaller and smaller. It's approaching 0. So if we take the limit as h approaches 0, and we'll just simply replace x naught minus x with h, this is exactly the same thing. And then, in order to get rid of the x naught here, we'll simply go, well, since h is equal to x naught minus x, we'll add x over and get x naught is equal to x plus h. So where x naught is, we can replace it with an x plus h. So this function with just x is equivalent to exactly our rate of change, which means this limit with just x is equivalent to our limit here with the x naught and the x. So we now have a way that we can create a function to find the instantaneous rate of change at any point on any given function where we can find that limit. Let's go ahead and take that exact same example we looked at before and show how this version and this version end up producing the same result. Here we have our equation that we used for dropping the ball from the Leaning Tower of Pisa with Galileo. 4.9 times t squared, we're looking for the velocity at 5 seconds, just like we did previously. Over on this side, though, we're using the derivative with the limit as h approaches 0, so our change of variables. As we work our way through, up here we have the x plus h and the x. Using our algebra with our identities, we get down here to the bottom, and we end up with 4.9 times 2x. Plug in 5 seconds for x, we get 49 meters per second. On this side, this is how we did it in the previous video, and we also get 49 seconds. The difference between the two here is that our x naught was a specific value instead of a variable. However, I do want to point out that if we used x naught here instead of a specific number, we actually would have ended up with an equivalent expression down here at the bottom. We would have been 4.9 and then x naught plus x naught, which would have been 2x naught. Very similar. In fact, exactly the same thing at that specific point. So you can use either version for the derivative, and there are differences because you'll notice that algebraically, while these are similar, over here we have a square polynomial and over here we have a difference of squares. So depending on the function you're looking at when you're taking these derivatives, there might be advantages to using one or the other. And as you're working through doing these things, you'll find that you might like one version or the other better. Most people tend to like this one, which is why it's become the standard definition for the derivative, as you'll see in just a moment. To wrap up our introduction to the derivative, here is our definition, which is just that the derivative of a function f at x is defined as the limit as h goes to 0 of f of x plus h minus f of x over h. Exactly our slope with the change of variable. Now, for notation, there are two notations that you're going to see most often. The Leibniz notation is the d dx of f of x. Now, this is not a ratio. This is considered to be the derivative operator. It is extremely useful, and you are going to see it a lot when you're working with integration, and it is very useful there, especially with change of variables in integration, or when we're working with the chain rule, something you're going to see a bit later, okay? However, you can see that it is a little bit clunkier to write because it's just bigger, it's a little bulkier. Also, when we're writing dy dx, sometimes, people when they're getting new into this can confuse it for being a fraction. And when we're working with it in integration, we do, in a way, treat it like a fraction. And when you start to work with multivariable calculus, you're definitely going to want to be working with the Leibniz notation, okay? The Lagrange notation is just a lot smoother. It's a lot easier, and most students do gravitate toward it. I will probably be using it most often when I'm writing things out quickly. So be used to seeing both of these. You will see both of these in most of your calculus classes also, and you'll probably see this one the most often, especially if you're ever doing anything online, because it is a lot easier to write an F with a comma than to try to write this out, okay? But do not throw away this notation. It will be extremely useful, okay? Now, the last thing that we need to do is go ahead and define something that it has taken well over a couple of thousand years, honestly, for math to finally get around to doing, which is a rigorous definition, finally, of tangent. Up to this point, there was really only kind of an understood definition, which was a line that touches a curve, but not really something you could do any computation with. And here it is. The tangent line to some function at a point is the line through that point, so the line through the x, f of x, with the slope that is equal to the derivative at that x, okay? So effectively, all this is saying is you take your equation for the line, take your function, find your instantaneous rate of change at that point. So do exactly what we did earlier. Take the derivative, plug in the x value at that point to find your instantaneous rate of change at that point. Plug that into your equation for the line. You now have a slope and a point. With that, you can finish out the rest of the equation. Okay? In fact, that's one of the problems you have as one of the exercises coming up next. So I hope that introduction to derivatives was helpful. If you have any questions, remember you can always drop down into the comments or join us on Discord. And as usual, the answers to the exercises will be after the outro.